the pond freezes over, and an icy frost forms on the branches of this pine tree. These small plates clinging to the pine needles are individual ice crystals. When water freezes, sheets of crystals come together in a seemingly irregular pattern. But ice has an inner structure that begins at the molecular level. This represents a water molecule. The movement of the molecules is slowed down by the cold, so if they get close enough, they will bond to each other. The magnet-like attraction between them makes them fit together so that they form six-sided shapes, hexagons. The molecules fit into the assembly like the pieces of a puzzle. These molecules are a small part of a piece of ice. The structure they make is known as a crystalline lattice, a three-dimensional grid based on the location of molecules that makes a repeating pattern throughout the ice. When water freezes and millions of molecules combine, the hexagonal geometry is still there. Now visible to the eye, it is a reflection of its own molecular substructure. This crystal formation is a process of growth in which water becomes a solid under the influence of cold weather. The ice on the surface of this pond has the same crystalline structure as frost. The texture and clarity of ice are determined by subtle variations in factors like sunlight, air temperature, and humidity. When turbulent winter storm clouds gather and the temperature begins to drop, the water vapor in the clouds freezes, forming small particles of ice that fall as snow. From winter blizzards comes one of the most delicate and beautiful of all natural structures, the snowflake. The snowflake is an ice crystal that forms the same way as the ice in frost or on the surface of the pond. Snowflakes come in many shapes, but if the structure of ice is always the same, how can there be such variety in snow? A snowflake is born when the moisture in a cloud forms as ice, often around tiny particles in the air like dust or salt. True to the hexagonal geometry of its molecular lattice, the disk grows into a hexagon. More ice forms at the 6 radiating points. Variation in conditions of the immediate surroundings lead to variation in shape. A branching pattern like this is most common when it's around 6 degrees Fahrenheit in the cloud. But even so, it is unlikely that any two snowflakes are alike because no two snowflakes form under absolutely identical conditions. When the humidity in the cloud is low, more plate-like hexagons like these tend to form. And the more ornate ones form only in a narrow temperature range and with higher humidity. As different as they may be, ice and trees both create branching patterns. The patterns come from the way the environment affects the materials they're made of and the way they grow. Entirely different influences may govern the growth of ice and plants, but they often end up with similar forms, such as the radiating spikes on these seed pods and on Queen Anne's lace. Even though natural objects are made of different materials, they can have related forms. And a single material can assume different structures under different circumstances. When water is frozen, it becomes ice. When subjected to other conditions, water makes other shapes. Running water is given no constant form by its internal structure. When it flows, it follows the contour of the stream's bottom and banks. It takes its shape from the conditions around it. The water pours smoothly over the fall. The turbulence below tosses water into the air. The water separates into a fine spray of many drops. The smallest ones are almost perfect spheres. We know that water forms drops, but why should drops form spheres? The surface of the water acts like a thin, elastic film. When this drop hits the water surface, a small crater forms. When the water rebounds to fill the crater, it surges upward, making a column. A bulb of water forms at the top of the column with a narrow neck below it. Its momentum carries it upward while the rest of the small column falls back and a drop breaks free. The film on the surface of the drop contracts, forcing its contents into the most compact shape that fluid can form, the sphere. The surface film that makes a sphere of a drop of water acts like the film of soap that makes a sphere of a soap bubble. This bubble is a skin of water and soap stretched around a volume of air. The air is as formless as the water, so the film around it tightens until it has packaged the air as compactly as possible. A sphere uses the least amount of surface material to enclose a given volume. Drops so small that their own weight doesn't distort them become perfect spheres. This drop is too large for surface tension to draw it into a sphere. But because of its relative strength, the surface film can be an impenetrable barrier to very small creatures like this copepod. Bubbles and drops are shaped by their size and by the tension in their own surfaces. Many living things, such as fruit like cherries and crab apples, also resemble spheres. These fruits are not formed by the same process as water drops and soap bubbles. And it is often less clear what the relationship is between their form and their function, or what advantage there is in these shapes. But there is a definite advantage in the form of these mallard duck eggs. Their oval shape is curved, somewhat like a sphere, and their shells make strong and efficient packages for the embryo inside. This is the edge of an eggshell highly magnified. It's made of these bullet-shaped calcite crystals with rounded points at the lower ends. Eggshells are not as fragile as they seem. They are strong from the outside and weak only from the inside. Like the stones in an arch,